All right, so I have our tentative order of our student presentations in our meeting chat. So we'll start off with Sarah. Sarah, you should have the share content button, so you should be able to do that now. And while Sarah pulls her presentation up, beautiful, Dr. Sackerman, I don't know if you want to say a few words or introduce our speaker.
Sure. So yes, thank you all for being here today. I think the first two talks speak to the interdisciplinary nature of graph theory itself. A lot of the research that's done in our department by undergraduates, some of it is done in graph theory, a good chunk of it. And so Sarah had approached me about doing something in abstract algebra. Perhaps, I said, well, there's partition theory, and that has a relation to the graph theory, and so we went with that. And then the next speaker, Annalisa, interested in immunology and healthcare issues and that kind of stuff, and we're also modeling that situation with a different type of graph. So without any further ado, I'd like Sarah to get started on partitions and degree sequences of even integers.
Can everybody hear me?
You're good, yep.
Okay, so my name is Sarah Hutchinson, and today I will be talking about partitions and degree sequences of even integers. This is the work that I started with Dr. Sackerman around last year's spring and summer. But all right, so let's get.
Sarah, I think you might have muted yourself.
Okay, I don't know why it decided to mute, but let's try this again. Okay, can everybody hear me?
Yes, you are doing good.
Okay. So I'm not sure where I cut off, but again, the definition of a partition, an expression of an integer n as a sum of smaller positive integers. And specifically, as I mentioned in the title, we are looking specifically at partitions of even integers, or as we denoted for shorthand, par2k. Now on the left, I have just a small example of partitions of 6, or par6, as I'll be calling it. And on the left, we have our 11 unique partitions of 6, each of which being in non-increasing order. So basically what we did was we took this concept and we looked at it from a graph theory perspective instead. And each of these partitions we now recognized as degree sequences. And so for each partition group that we looked at, each of the partitions fell into 3 main families. The first of which, let me get up my laser pointer. The first of which here is where the first degree in your sequence is larger than the sum of the rest. For the second family, this is where your first degree is equal to the sum of the rest. And for the last family is where your first degree is less than the sum of the rest. And for each of the partitions, we came up with 2 visual representations. The first of which is through a Farrer's diagram, which is a concept from number theory, where the number of rows represents the number of elements in your partition, and the number of dots or boxes in each row is that numbered element. And then we also came up with a graphical representation of each one. And here, now we see this as the number of rows is equal to your number of vertices, and the number of boxes in each row is now your degree of that vertex. So each of the 3 main families had a bunch of unique properties. So for the first family, every single graphical representation was a form of pseudograph, whether it had multi-edges or it was just a pseudo-simple graph. But each of these graphs had 4 self-loops, and none of them had any split realizations. So an example here is just 411, again from par 6. Now, for the second family, this is the point where you stop seeing any kind of forced self loops in your graphs. And specifically for the second family, all of your graphical realizations are a multigraph, so with the exception of the simple star graph seen at the end of the family, which for this example specifically would be 311, which is not pictured, but and this is also where you start seeing your split realizations pop up as well. So every partition or now degree sequence in your second family has a split realization, which is basically just, for those of you who aren't familiar with graph theory, is when you split your graph into your clique nodes, which are all connected to each other, and then your independent set, which are not connected to other vertices in that independent set and only to the clique nodes. And then for the third family, this is more of a mixed bag, and there's actually a lot of diversity you can see in your graphs for the third family, but because par 6 is such a small sample size, you don't get to see all the graphs that can potentially form. But for the most part, you see multigraphs, you see simple graphs, either one of those having split realizations or not. And then towards the end of your partition set, you also start seeing your disconnected graphs pop up as well. Now this all accumulates to the formation of our lattice, which previously, if you attended my presentation last semester, we called a Hasse diagram. But through further study, we actually found out that it is actually a lattice for reasons I will get into in a little bit. So yeah, this is our lattice, and as you'll notice, each numbered box corresponds to a specific numbered partition, and then each of these 3 colors represents each of our 3 main families of partitions. The one you see at the top here is our first family. These are the pseudographs. And then this next one here, this is our second family. And the one shown at the bottom left is our third family. Now this, I guess, ordering of our lattice is consistent for every partition set that we looked at. The first family will always fall on that upper right section of our lattice, with the second family falling in the center, and then our third family falling at the bottom left. And you'll also notice that the boxes outlined in black are our split realizations, and these always fall directly in the center of our lattice. And then the blue lines I just included here are just dividing the split from the non-split. And you might be wondering, well, how did we set up this ordering in our lattice? And the answer to that is through majorization. By comparing each of our partitions or degree sequences through majorization, we are able to form a ordering or a hierarchy amongst our partitions. And I will show a quick example of this. So here we're going to show that partition number 7, or 3111, majorizes partition number 9, which is 2211. And for this to happen, each iteration of a partial sum for partition 7 has to be greater than or equal to that of partition 9, and then they both their sums have to equal at the end, which I showed in this rightmost column here. This is true. And then when we go back to our lattice, you will see that partition 7 is placed above partition 9, and then the black line shown here, it indicates that relationship. And this is how we figured out the ordering for our lattice, basically. And then also, in order for majorization to work, the length of your degree sequences have to be the same. And for my example, I picked 2 partitions that were the same length, but when we compared each of the partitions in this set against each other, we added zeros in order to make them the same length. And since we're only looking at the sums part of the majorization definition, this is what allowed us to do that. And as far as our bounds go, this is what specifically makes this a lattice. Each of our partitions here have a least upper and the greatest lower bound. Yes. And then here are my references, but I also wanted to talk about what makes this research so unique, I should say, is that we base a lot of our work off of the work of Russell Maris, specifically in his paper on split graphs, specifically this one. And though he also kind of worked with the Hasse diagrams and the partitions, he more so focused on the simple graphs and the simple split graphs as well. But we decided to also look at and consider our pseudographs and multigraphs, which aren't normally considered graphical, but we decided to include them anyway. And I wasn't able to show it here because of time constraints. But when I was able to list out all of the each partition and then their graphs and then their split graphs and their Ferris diagrams, you were able to see just the what's the word, evolution of how your partition works. And hopefully in my next presentation next week, I'll have a little bit more time and I'll be able to show that. But for now, this is what I have. And thank you for listening.
Thank you, Sarah. I wanted to open up the conversation for any questions that you may have for Sarah. Okay. All right.
I guess I can ask one, Sarah. What keeps this from working well for odd numbers?
Oh, I mentioned that in the beginning, is that the reason why we need to use even integers specifically is because of the first theorem of graph theory. I'm not sure if that's when I cut out before, but for the first theorem of graph theories, where the sum of the degrees is equal to twice the number of edges, which is why we're looking at partitions of 2K specifically. Because I did attempt just for fun back last summer to try with even integers, and it, like, through a number theory perspective only, it would technically work, but because we're looking at specifically through graph theory, the graphs themselves wouldn't hold up to that definition, if that makes sense.
Yes, that makes sense.
Okay.
You could, of course, look at a subset of par 2K and just add a 1 to everything, but very good work.
Thank you.
Okay. All right, I don't see any other hands, so we will move. Beautiful job, Sarah. We'll move on to another one of Dr. Sackeman's students, Annalisa. So Annalisa, if you would get your presentation all queued up, we're ready when you are.
All right, can everybody hear me okay?
Yep, you're good.
Awesome. Okay, so I'm Annalisa Espino. I'm a senior math major, and for this research project, I wanted to look at immunology and network flows with the help of Dr. Sackeman. Okay, so first, some background information. We decided to look at directed graphs or digraphs, and this is a graph that has edges that go in a certain direction. So for example, in node 1, the edge travels to node 2, and it only travels in that direction. We also looked at 2 other types of transmission. First, a double transmission. So this is when the edges have a certain weight to them. 6 has 2 edges going to node 4, so the weight of this edge is 2. Here is double end transmission, and in this case, we have 1 edge going from node 1 to node 5, and another edge going from node 5 to node 1. So these are 2 separate edges of degree of weight 1. So that's the difference between these two. The main difference is the weight of the double transmission. It has a double transmission weight of 2, and this one only has a weight of 1. So our research question was, if these digraphs represent people through the nodes and disease transmission through the edges, can we find a pattern in the digraphs that have the highest rate of disease transmission? So when we looked at different digraphs, we found a pattern in which ones have the highest rate of transmission. First, we wanted digraphs that didn't have a source or a sink. We wanted double transmission instead of double end transmission, and we wanted a modified block circulant adjacency matrix. So this is how we calculated our energy. First, we started off with a graph, and we took the adjacency matrix, and this is a little bit different from other adjacency matrices since it's not a symmetric graph. So node 1 goes to node 2. Looking at column 1, there is a number 1 in the second row, and that's how we created this adjacency matrix. Then we took the eigenvalues to calculate the energy, and in other areas of graph theory and chemical theory, I believe, we have energy as the volatility of a graph. And in this case, we're using energy and applying that definition to be the infectiousness and the rate of transmission within that graph. So for energy, usually you add the real parts of the eigenvalues to get your energy. And that's what we did on the left, and we had this number. But we realized that our eigenvalues were made up of real and imaginary parts, and we wanted to incorporate these imaginary parts into our energy to see if it added something. And that's why we took the modulus as well. And that is when we have this energy on the right, which is higher than just our real parts. So looking at sources and sinks, a source is when a node is transmitting its edges, and in this case, its infectiousness to other nodes, but it's not receiving any. So in this case, node 4 would be our source because it's transmitting to nodes 1 and 5. And in our second example, we have a sink, which is the opposite of a source, where it's receiving all the infectiousness, but it's not transmitting it out. And in this case, it's node 5. So what we noticed here is that the energy between source and sinks are very similar. So we decided to look at a graph that had both source and sink. So in this case, node 2 is our sink and node 1 is our source. And when we looked at this, the energy had 0. So we determined that we didn't want any graphs that had source and sink because this gave us an energy of 0, and we wanted to find the highest transmission. Next, we looked at double or double end transmission. So in this graph on the left, C2, you'll notice that all the edges are double transmission, meaning they all have a weight of 2. And you can see this here in the adjacency matrix, where all the numbers that aren't 0 are 2. So this signifies the weight of those edges. And when we added up our real parts, we got an energy of 16. Now, if we look at our double end transmission, here you'll see that all of the edges are double end transmission. And this is, like I said in the beginning, edges that have a weight of 1. So you can see here, there are more edges, but they all only have a weight of 1 versus double transmission, which has a weight of 2. And when we took this energy, it had an energy of around 9.7. So we realized that the weight of these edges matters more than the number of edges. If you have more edges and the weight is only 1, it's not as significant as less edges with a weight of 2. And then our last thing was a modified block circulant matrix. On the left, you can see a definition of a block circulant matrix. Now on the right, we looked at a sort of modified version of this. So here are 2 matrices, and on the next slide, you'll be able to see what those graphs look like. But here, with this matrix, we can split it up into 4 separate blocks. So this block on the top left and on the bottom right are all 0. And on the top right, we see that our main diagonal is all 2. And at the bottom here, it's not a main diagonal of 2. And we wanted to get it to be that and see what happened and how the energy changed. So what we did was we moved this 2 up within the block and everything else moved down, giving us this new matrix. And now you can see here the matrices and what they look like. So with the original one, you can see here, everything is double transmission. The weight is 9.7 without the modulus. When you incorporate those imaginary numbers, it's 16. Now, in this one, where we have main diagonal within the block, and it's almost mirror images of each other, both with and without the modulus, so only adding the real parts and incorporating the imaginary parts as well, we have 16 as the energy. And we believe the reason this is because not only do we have all double transmission, but the energy and the rate of transmission is much more concentrated. So here, all the rate of transmission is within these 2 nodes and within these 2. Whereas with this graph on top, you can see the rate travels from 5 to 1 and then to 8. So there's a lot more traveling happening versus in this graph. So if we want the highest rate of transmission, we really want everything to be concentrated together, and we want a weight of 2. And here are my references. Does anybody have any questions?
Okay, I see a question in the chat from Donna. Donna asks, if the graph size increases, will the energy still stay 0 with the source and sink?
Awesome. I'm going to go back to that slide. Okay. So here you see that we have 6 nodes and we have 8 edges. So we also looked at graphs that were 8 edges, or 8 nodes, I'm sorry, and 12 edges. And what we noticed here is that if there was 1 source and a sink, it gave us a very low energy, but it wasn't 0. When we did 2 sources and 2 sinks, that's when we got an energy of 0. And that kind of increased. So as the number of nodes and edges increased, the number of sources and sinks that you need in order to get the energy to 0 had to increase as well. But even if you just had 1 or 2 in the case that you increase more, it still is very low and not significant enough.
Okay. All right. I don't see any other questions. Wonderful job, Annalisa. Thank you.
Thank you.
So next up, we have some group presentations from Dr. Luttrell and Dr. Lonin. So the first group up will be William, Donna, Eden, Brooke, and Joshua. So whoever is queuing that up. And while you are pulling that up, Dr. Luttrell, I'm not sure if you want to introduce your students or say anything.
Absolutely. Thank you, Tara. Thank you, Professor Wager. Thank you, everyone, for coming today. This year, I have had the honor and privilege to work with a team of very talented undergraduate students, along with my good friend, Dr. Thomas Lonin from Stevens Institute of Technology, on 2 research projects. The first project that is being worked and completed by Donna D'Alessio, William Mole, and Brooke Mullen from Seton Hall University, and then Eden Lovicius and Joshua Renai from Stevens Institute of Technology. Their talk is on machine learning and clustering techniques for resectoring stocks with categorical data. And the following presentation will be research done by Elizabeth Puskas from Seton Hall University and Michael D. Pentima and Ayush Patel from Stevens Institute of Technology. And their title is Short-Term Regime Switching Option Pricing. So with that, I will turn that over to our first group.
All right, is everyone able to see the screen?
Yes, you're good.
All right, perfect. So Dr. Luttrell did a great job introducing that project, and the one that we're presenting on today, me, Donna, Will, and Josh, is titled Machine Learning and Clustering Techniques for Resectoring Stocks with Categorical Data. So just a bit of background, the stock market is currently presented as a weighted collection of 11 sectors. These sectors are energy, industrials, utilities, healthcare, financials, consumer discretionary goods, consumer staple goods, information technology, communication services, and real estate. And what this pretty much means is that every company on the out there is put into one of these sectors based on the primary service that it offers. And this is quite intuitive, but it becomes increasingly less so as companies like Google, for example, continue to innovate and expand their product offerings. So at a time, they only offered a search engine service, and now you'll see a whole host of new products that they're offering, which begins to raise the question of if this sector classification is a bit too arbitrary. And this is especially important when considering modern investment theory, because portfolio diversification is largely based on these sector classifications.
So this raises the main question of, is there another way to draw these sectors that better reflects the underlying similarities and statistics of these traded companies? And should the current method of these arbitrary functions be the main determinant of these sectors? So this research is, if the answer to that question is no, how can we improve the portfolio diversification through computational and data-driven techniques? And Brooke, put it on the next slide. We propose that the best approach is through data. And as Donna will describe, we wanted to maintain objectivity in our approach, so the methods we used in obtaining and trimming the data into a usable state were done with the interest of maintaining integrity of this data.
Okay, so we started with 78 non-dividend paying stocks from Barron's.com and 97 dividend paying stocks. And then once we put these through the Wharton Research Data Services, only 171 out of the 175 were returned. So the data that we chose to focus on was fundamentals quarterly from the years 2010 to 2020. These years were chosen arbitrarily, and we chose quarterly because it creates a better picture of the stock performance in comparison to annually by using shorter time scales. So why we chose the year 2010 was because given the technological advancements for data collection and given our growing understanding of this field, it's got easier to guarantee that we will have a more consistent data set for these given years. So we started out with 1,793 variables, and then we went through the process of eliminating them. So those that were eliminated consisted of had the following traits. So if they were not listed in WRDS's variable descriptions for fundamentals quarterly with daily updates, they were eliminated. Also, if they were containing no outputs, and if those containing all outputs to the same value, text, number, or other, they were also eliminated. And we also went back and eliminated the ones that had more than 10% of the corresponding outputs missing. So after going through the elimination process of these specific variables, we were left with 213 of them. So the examples of what these variables were that we had, some of the examples were that we had high frequency price data. So this is data collected at an extremely fine scale, which is tick by tick. We also had capital assets held And along with this, we also had softer data, which included phone numbers or zip codes.
These are some initial graphs that we made looking at the data we collected. These two were just taking the first 10 stocks we had alphabetically. So you can see like AL, APL, etc. And we looked at just accounts payable and cash holdings, just because we thought they would be interesting things to look at. The main thing you can see that is the main interesting thing on these graphs is that there is one stock that goes absolutely crazy, unlike all the other ones, which is Apple. Big shock. All the other amounts, I believe these amounts are in like thousands, so like don't even kind of hit like thousands of dollars. But Apple just shoots right up there in both graphs. And so since we're coming at this from a data-driven perspective, and we're going to be specifically looking at these numbers, one thing that we may end up seeing happening, or the thing that may be telling us from these graphs, is that stocks like Apple and Google and Amazon that are very spread very widely in the things that they do, and have a lot of holdings and things like cash holdings and accounts payable and all the other financial data that we collected, may just end up becoming their own sector by sheer size of numbers. But how are we going to actually split them up? Brooke, if you go to the next slide. So to actually do this data-driven approach, we're going to be using what is called unsupervised machine learning. So machine learning can broadly be broken down into two types: supervised and unsupervised. Supervised, the main difference is whether or not we already have the answer, I guess, known. Supervised machine learning is where we have both the answer and the problem known. For example, say we want to price houses in New Jersey. So we have a bunch of data on the different types of houses, like number of bathrooms, square footage, when was it built, etc. And we also know the price it's currently at. We can train a model to look at that, and then if we give it new specs, it can then spit out a new price, or like what it thinks the price should be. But obviously we don't want to know the answer ahead of time. We want to see what the model will decide are the different sectors based on the data we give it. So for that, we turn to unsupervised machine learning, which, as I'm kind of implying, just is machine learning models where we don't know the answer ahead of time, and the model gives us an answer that we have to interpret. The main type of models we're going to be using for that, or we've been looking at, are clustering models, which, as the name sounds like, clusters similar-looking data to each other. There are two main algorithms within that we're looking at: hierarchical clustering and k-means clustering. Hierarchical clustering, as the word hierarchical implies, builds a hierarchy of the different clusters, where it is an algorithm that starts by grouping an arbitrary point from the top, the master all the data grouped into one group, and then works its way down. And it will end when each cluster is distinct from each other cluster, and when all the objects within each of those clusters are broadly similar to each other. There is a main problem with this, though, and that is that it's building different hierarchies. We don't so much care about how they act hierarchically as much as we just care, what are the different sectors. But it will also just, as a good thing, it will create as many sectors as it deems necessary. And I specify this because that is the drawback with k-means clustering. K-means clustering is an algorithm where we specify an amount of groups we want to make, and it will determine what data is closest together that will fit within those k groups. It starts by creating random points on the graph. So say we have these this graph is an example. We have these two markers in the red zone and the green zone. Say those markers weren't there. They were just in the random white space. From there, it would decide which data points should belong in each of those groups, calculate the variance within each of those groups, and then calculate what the actual means probably should be, and then it updates where those markers should go. And so the idea of the algorithm is that we're actually trying to move those black markers around until there's a little variance within them. Obviously, that's very good for what we want. But the drawback is we have to specify how many clusters we want at the beginning. As in, we would have to specify how many sectors we would want before we even started running the algorithm. A way to potentially fix that is to just simply run the algorithm a lot, with a lot of different cluster sizes, and seeing what will happen. Clusters. But yeah, that is mainly what we're looking to do.
So as Josh explained, once we've determined these new sectors, In order to determine the efficacy of this approach, we endeavor to show that portfolios consisting of the elements of our derived sectors have less risk than portfolios of existing sector divisions. Some interesting aspects of this are the stability of these sectors. Because we're dealing with high frequency data, things are bound to change as we saw in the graphs that Josh discussed. So those are some interesting things to think about with this approach. Yeah, we'd like to thank Seton Hall University and Stevens Institute of Technology and Dr. Luttrell and Dr. Lonin for spearheading this and helping us all along the way.
And Donna and I, as CBL scholars, would also just like to thank the program for supporting us throughout this process.
Okay, wonderful job. Do we have, I think I see a hand up. Dr. Marlowe.
Are you guys doing anything to make this into a product? Do you have some sort of intellectual property designs on what's going on here?
Right now, we're in kind of a proof of concept phase. We don't have any results that we can say that our sectors are demonstrably better than the existing ones. Our goal is to reach that point, and we can discuss that when we get there.
Okay, any other questions? I don't think I'm seeing any hands, and let me check the chat. Okay.
Not that important.
Gotcha. Okay, I think we have our next group, which is Elizabeth's group, the second group of Dr. Luttrell and Dr. Lonin.
Can everyone see my screen?
Yep, you're good.
Okay, perfect. Thank you, Professor Wager. Good afternoon, everyone. I am the second half of the group of Dr. Lonin and Dr. Luttrell. I'm presenting on behalf of the short-term regime switching option pricing group here today. So starting with our objective. Our objective with this project and our ongoing research in this process is to test the different calibrations of short-term regime switching volatility and attempt to outperform the Black-Scholes model. Now, what exactly does this mean? So starting with the Black-Scholes model, that's basically the standard right now that the financial industry uses in order to predict option pricing. And we'll get into a little nitty-gritty of what these finance terms means in a second. The second thing I would like to point out in this objective is the volatility. So what exactly do we mean by volatility when we're talking about this? So how volatility basically works is it's the variation of prices of certain assets over time. So a real world kind of relatable example is COVID. COVID has obviously taken the world for a spin and in unprecedented times. So what has happened with the stock market, it's caused prices to fluctuate all over the place because people don't know exactly how to react to it. That's an example of extremely high volatility. But in more stable times when the economy is kind of, at a more standstill, then we would have less volatility there. So some financial lingo, starting with options, the security that we're working with. An option is a type of financial derivative. What a financial derivative is, it's a security in which its value is based upon an underlying asset. So in this situation, for our project, we're working with options of stocks. So the stock would be the underlying asset. As the stock price moves, the option's value also moves accordingly. The option itself
is the right but not necessarily the obligation to buy or sell a stock at a certain price. This certain price is also known as the strike price, or the exercise price. That's important to know coming up. The second thing is the bid-ask spread. What the bid-ask spread is, it's the difference between the highest price a buyer of an option is willing to pay to buy the option and the lowest price that the seller of an option is willing to sell the specific option at. So in our process to, kind of just to delve into our objective, we had to collect historical data. Originally, we wanted to look at non-dividend paying stocks. By dividends, I mean it's when a stockholder is given some part of an earning that a company would make. Typically, stocks are dividend paying. So when we tried to look into non-dividend paying stocks to eliminate some of the extraneous variables, we found that our sample pool or sample size wasn't very big. And because of this reason, we decided to expand into dividend paying stocks. The main thing that we needed, though, from these stocks, whether they were dividend or non-dividend, were that they were high frequency, so they were being traded often. We decided to look into minute historical data. Now, typically with options in the US, they are tracked on a day-to-day basis, which meant finding minute historical data kind of a struggle to find. We were able to luckily find a foreign source that did provide previous option prices on a minute-to-minute basis. However, because it was a foreign source, we were dealing with almost 100 companies over a span of 6 years, dealing with minute data, and time zones were all over the place. So a big thing that we've had to do, in addition to finding a source and then sourcing all of that from there, is converting all of it into what we know as Central Time, and it's what the US uses and its exchanges, such as the New York Stock Exchange and NASDAQ, uses in order to compare apples to apples instead of apples to oranges. Black-Scholes, as I mentioned earlier, is the standard of what the financial industry uses in order to predict option pricing. What I have added here is the function itself and the variables. Here you can see the stock price that I mentioned earlier, which is the price at which the option can be bought or sold. The strike price, I'm sorry. But the main thing, again, that I want you to focus on here is the volatility. What we're trying to do in this whole project is to look at the frequency. Typically, when we use this model, as it is used now, the rate used is an annualized rate, and which, in other words, basically means it's not tracking a volatility that's equal to a minute level. It's more broad than that. So when you have more variability across, it's not taking into account the smaller time increments. What we're trying to do by looking at the minute historical data is to look at the frequency there and then apply to this formula to see if we can more accurately predict option prices. And we would do this by comparing what we got to the historical data we found and seeing if it falls within that bid-ask spread that I mentioned earlier. So what is next? So moving forward, now that we were able to compile the data and make it usable for our purposes, we're going to continue to try to test different calibrations and different volatilities within our model to see if we can do better than Black-Scholes as it is now. And that's in addition to looking at the volatility and also taking into account the time until maturity. A good way to think about time until maturity is think about a coupon that you use at a grocery store. At a certain point, it expires and you can't use it anymore. The option works the same way. At a certain point, it can no longer be exercised. So by taking into account both that minute level volatility and the time left until the option expires, we're going to see if they're going to see what we can do. Thank you to both the CVL for supporting my endeavors, as well as my counterparts over at Stevens and all of their work, especially with the coding. And also thank you to Dr. Lonan and Dr. Luttrell for helping us on this endeavor. Are there any questions?
Dr. Marlowe.
Everybody deserves one question, at least. So I know this is fairly standard, but how do you take account of dividends in the model?
The main thing that we're looking at with the dividends for our purposes is to make sure a stock split, of course, would do something that would affect the stock price as well as the volatility, because a lot of with the stock market, it is a reaction to people's expectations of the market, and dividends do add an extra variable of people's reactions that we are trying to, in a way, assuage when we're trying to predict something new. Did that answer your question?
Well, the other thing is the price before a dividend is paid is, of course, higher than the price after the dividend is paid, the price of the stock. So is that is that reflected in the option price, or if not, how is it reflected in the model?
I'm not 100% sure, only because we haven't gotten to that stage yet. As far as I know, the data we've collected looks solely at the stock price and doesn't take into account the dividend. But I think for our purposes, the main thing we were looking at is to see how the dividends were going to affect the stock price and thus our results on all firms.
I can also throw in just a tiny clarification.
Thank you, Dr. Lonan.
No worries. Our focus is on short-term options, so expiring within a week. So we're not really going to try and price assets that will pay dividends within that time frame. So it's more of a extremely short term, to the point where we can just completely ignore the risk-free rate, because we're talking about 3 or 4 days.
Okay, so the dividends would either be anticipation of a benefit or enthusiasm because of success, or the converse, rather than anything else.
Right. Well, the dividends will only really come into play as far as pricing these options if a dividend payment occurred during the lifetime of the option, in the remaining time of the option. And since we are going with such a short time frame, we're just going to ignore the ones that would have a dividend payment actually within the window that we're looking at.
That makes a lot of sense. Thank you.
I have a comment or question to. It's my understanding, of course, that these are pricing, sort of at the market. This is a pricing at the market formula that, is sort of the best estimate with Black-Scholes of what to sell the option for within the period before its expiration. But am I correct that Black-Scholes is assuming that we have American-style options that can be exercised anytime up to and including the expiration date, as opposed to European options, which can only be exercised at the closing date?
So the focus is on European options, but for non-dividend paying stocks, the European call option price will be the same as the American call option price.
This will only be exercisable at the closing at the expiration date of the option, not at times in between. You can't exercise, say, a call option of this type between the time that it's issued and the closing date. Correct?
Right. Yeah. So, like I said, we are focusing entirely upon our on European options, even though typically what is in the market is American options. But as I said, under certain assumptions, which are the assumptions we make, the European options and the American options will always have the same price unless it is a dividend paying stock, as Dr. Marlowe was asking about. So we're just going to ignore those that pay dividends during that time. And so then our European and American options would be the same.
Wouldn't be much different anyway if they're expiring in a relatively amount of time anyway. Because
exactly.
Yeah, but if you had a longer period of expiration, if there were long-term options, leaps, for instance, then the difference between European options and American options, the pricing difference at intermediate points, if you don't exercise them but just buy or sell them, would be quite a different, correct?
Yes. So in that case, we would probably try to do some sort of finite difference methods to actually be able to price the American style options. But to sort of intentionally not do that, we are putting our focus specifically on short term.
Okay, sounds good. Thank you very much.
No problem. Sorry to intrude on you, Elizabeth.
Okay. All right. Wonderful job, Elizabeth, and your group too. I think we're going to move to Dr. Kale's students. So Marie, you're up next. Dr. Kale, I'm not sure if you wanted to introduce your two students, or I know they're not in a group together, but if you wanted to say something before they started.
Sure, love to. I'll try to keep it brief. I know we've passed the midpoint here. Marie's working on a project she first started working on last summer. She was the recipient of a New Jersey Space Consortium grant, so she's been working on that since. And Evan has the distinction of being one of the few students to come to me with a problem that he wanted to work on, rather than me kind of devising one. As you'll see, it's a problem he encountered in Journal Math Horizons about a year ago that still does not have an answer. One of the few problems I've seen them publish the answers, saying, basically begging for some kind of progress on it. As you'll see, he's made it quite a bit.
Okay, thank you. Marie, if you're all ready to go, we're ready for you.
Okay, perfect. I'll just get the PowerPoint.
Sure.
There we go. Can everyone see in here?
Don't see it yet.
Not yet, not yet. I think it's going. Yes, you're good now.
Oh, okay, perfect. Okay, so I'm going to be talking about building extremal networks. This is a project I've been working on with Dr. Nathan Kale over the past school year and starting over the summer. So first, I would like to thank Dr. Nathan Kale for acting as my advisor throughout this. I'd also like to thank the CBL Scholarship Program for supporting me throughout this process, and I'd also like to thank the NJSGC NASA Fellowship for funding me over the summer. So for my objectives, I'm going to first introduce my topic by bringing up what network strength is, toughness, and threshold graphs, because they're important to presenting the question that we're approaching. So then I'm going to present the question, and then I'm going to get into our findings with an example, just for the sake of time. So network strength is just one way to measure graphs. So we want to find extremely strong or weak graphs. That's what we're looking at, and our research is focusing on specifically extremely weak graphs because it has proven to be more difficult to look at extremely strong graphs. So we figure that looking at what weaker graphs would look like would provide a better picture of strong in the future. So we're measuring graph strength with a measure known as toughness. So for the purpose of our research, we're looking at specifically just that measure. So toughness measures how badly a graph can be broken up when some of its vertices are removed. So if you look at that fraction on the bottom, there's a lot of variables, but what it's basically saying is the numerator x.
Marie, we're only seeing the title slide as far as I can tell.
Thank you. I was just about to cut in. Yeah, we're only seeing your title slide there.
Can you see the toughness slide now?
No.
Unshare and share again. Sometimes that works.
Okay. Okay. Are we good now?
Okay,
It's loading and it looks like you can change them.
Try advancing your slides. Okay.
Marie, if it's not letting you change, if you'd like, I can try and navigate them forward. Is that working for anybody else?
No, not on my end.
Oh yeah, if you could do that, please.
Is it? No, are you able to see this, Tara, if I switch them forward?
I'm still seeing Marie's screen. Okay, hold on, let's see.
Because I was trying to push them forward for her.
I think I sent the PowerPoint, so I could try sharing my screen, actually.
I think I have it real quick.
You
Let
have
me,
it?
I don't
Okay.
mind putting it up real quick.
All right.
Include audio. Marie, is that working for you? Or are you guys seeing it scroll through now?
Yeah.
Yeah. Yeah.
All right,
Thank
so
you.
all right, so we can just give me a next slide, please, and we'll do what you need.
Okay. So we did this slide. So we did that one too. That one, and then I went over network strength, so we can go to the next slide. Okay. So for toughness, it basically just measures how badly a graph can be broken up when some of its vertices are removed. There's a lot of variables in that fraction. So what it's basically saying is the numerator is how many vertices we're removing in order to make the graph disconnected. The denominator is how many pieces are left behind that are disconnected from each other. And because we're looking at weakness, we're looking at the minimum. So if you're looking at all of the possible toughnesses that can come from removing specific amounts of vertices from a graph, the minimum would just be the smallest fraction that could be made. So for our purposes, we're examining the weakest graph. So the smaller this measure, the weaker the graph is going to be. You can go to the next slide. So we're looking specifically at threshold graphs for our research because Dr. Kale found that extremely weak graphs are always threshold graphs. So we're just expanding on that. And to briefly describe what a threshold graph is, we have the example right there with the notation of 4, 1, 2. Basically, what that is saying is there are 6 vertices in this, and they are split into 2 types. There is the clique vertices, where all of the vertices inside that clique are connected to each other by one edge. Since we're looking at simple graphs, it's going to be at most one edge between any pair of vertices. So all of the vertices inside the clique have one edge between them. And then there's the independent set, which is the vertices labeled 1 and 2. Basically, for the independent set, if you take any 2 vertices within that set, the neighborhood of 1 is going to be nested within the neighborhood of the other. So that's all we need to know about threshold graphs. So you can go to the next slide. So looking specifically at the toughness of this graph, if you look at the bottom left image, removing 1 clique vertex makes 2 disconnected pieces, so that makes the toughness 1/2. Basically, we're removing clique vertices because it's easier to disconnect the graph by removing clique vertices. It also provides a smaller toughness. So if you remove independent set vertices, then that won't disconnect the graph as easily. So that's why we remove clique vertices specifically. And if you remove 2 clique vertices, as you can see in the bottom right image, that would disconnect the graph into 3 pieces. So that makes the toughness 2/3. Since 1/2 is less than 2/3, our toughness is going to be 1/2. You can go to the next slide. So we're looking at specifically the weakest simple threshold graph, so that with all this in mind, our question is, given a specific number of vertices and edges, NM, can we determine what our most extremely weak threshold graph would look like? So a lot of threshold graphs can be made by just having the number of vertices and edges that you can make graphs out of. So we're just trying to predict exactly which ones would be our weakest ones and the toughness that would come from that. So next slide, please. So we had an interesting solution come out of this. We actually had 2 kinds of graphs that would come from the relationship between our vertices and edges. And we found this by looking at how many edges away from a complete graph we are. So if you have n vertices, you're going to have n choose 2 edges if you had a complete graph. But n choose 2, for example, -11, that is saying that you have n vertices And then for the amount of edges, it would be n choose 2, but minus 11. So there's 11 edges missing from a complete graph. That's our capital M. And looking at the patterns from this relationship between our vertices and edges, we found there are two kinds of graphs that would make our weakest graph in terms of toughness. So we have our balance graph on the left, which is basically you're trying to have as many vertices outside of the clique as possible. And among those independent vertices, you're going to have about as evenly split edges coming out of them. So all of the degrees of all of those vertices are going to be about equal or close to equal, maybe like 1 degree apart from each other. So we have n-6 and then a bunch of n-5s for this specific example. And there's going to be n-4 vertices on the inside. And then for our unbalanced graph, we have as many vertices inside of the clique as possible. So ideally, we would have n-1 vertices inside the clique. Sometimes that's not possible depending on what our amount of edges given are. But otherwise, if there's more than one vertice outside of the clique, then we're trying to have as many vertices outside the clique of degree 1 as possible, because that makes a smaller fraction, because the numerator would be 1. So that's it for that slide. And since we have two types of graphs that are being produced that could be the weakest, the next question would naturally be, when is which graph weaker? What values of n and m would that be? So if we're looking at so if n is less than that value k times that capital M-1 over k-2, the k is like the clique size. That is basically saying that the unbalanced graph would be weaker, and if n is greater, then it would be the balanced graph. So I don't really have enough time to get into how we got to this conclusion, but for n choose 2 minus 11, for example, the unbalanced graph is weaker when n is less than 16, for example. Go to the next slide. So let's look at an example where we have an actual value for n, which would give us a value for m. So if we have n equaling 10, we have two types of graphs that would come from this, the balanced and the unbalanced. The balanced is going to be the one, that top image that has the 4 and the 5s. And then the unbalanced is going to be under that unbalanced on the very right. So for the balanced toughness, if you remove 4 clique vertices, that's going to make two separated pieces. As you can see in the bottom left image, that makes our toughness 2. If you remove 5 vertices in the clique, that's going to separate our graph into 5 separate pieces, and our toughness would be 1. So for the balanced toughness, that would make 1. And then if you look at the unbalanced graph, it's I didn't make separate images for that one because it was easier to see the disconnections there. But the toughnesses would basically come from removing 1 clique vertex and then removing 5, making the toughnesses 1/2 and 5/3. Desired toughness would be 1/2. And because n is less than that value I had in the previous slide, it is true that the unbalanced graph is going to be the one that has the weaker toughness. And that's basically it for that slide. And here are my references, and I would like to thank you for your time, and sorry about the technical difficulties.
No worries. Dr. Marlowe has a question for you. Go ahead, Dr. Marlowe.
Do you ever get ties where the unbalanced and balanced thresholds just happen to hit at the same toughness, or does it always one or the other?
There actually are some times where there is a tie between the two. I wish I could show like this. We made this giant chart that kind of had like where exactly n would switch between the balanced and the unbalanced, and in some of the cases there was a tie for a very specific like value for n and m. But yeah, that is the case sometimes, but usually that would be the switch off point.
Dr. Kale, I thought I saw your hand up, but I could have been imagining it.
That was entirely an accident. I was trying to clap.
Okay. All right. Well, that's any other questions? I was going to start clapping too. Yeah, see some more clapping hands. Awesome. Okay. All right. Nice job, Marie. Thank you so much. Thank you. Thank you. Our next presenter is Evan. So Evan, if you're all ready to get yourself queued up.
Is it sharing my screen?
Yes, I
Okay.
see it.
So Today, I'm going to be speaking about a problem that Dr. Kale and myself have been working on during the course of this semester called dense dominoes. So in this problem, we're going to consider having D dominoes arranged in an integer grid with no dominoes overlapping and having the objective of the arrangement of the dominoes to be to minimize the perimeter of the rectangle that encapsulates all the dominoes. So with this, we're going to have two cases. We're going to have our non-restricted case, which has no restriction on the arrangement of dominoes, and we're going to have our restricted case, which says that no two dominoes can share an entire long edge. What we're going to do is we're going to compare these perimeters, and we're going to find when the perimeters are different for any number of dominoes. So the initial formulas that we're going to start with are just area and perimeter, and we found that area is going to be equal to 2 times the number of dominoes, since each domino is of size 2. There's some pretty simple optimization. In calculus, we can find that length is going to be equal to width, which is equal to the square root of a. However, if we look at certain number of dominoes, such as when we have 10 dominoes, we're going to have length equal to width equal to the square root of 20, and square root of 20 is not an integer, so that would break our integer restriction that is required from the initial constraints of the problem. So what we need to do is we need to move from our optimal solution into an integer plane. So now we're going to be moving into that non-restrictive case that I talked about on the first slide of the problem. So we're going to consider S being the sum of the dimensions length plus width, and we're going to have S of n, which refers to S of the non-restricted case, be equal to the ceiling of length plus width of the optimal solution. So now we're going to consider when S of n is even and when S of n is odd. So when S of n is even, we're going to have length equal to width, and when S of n is odd, length and width are not going to be equal to each other because you can't add two numbers together that are the same and have it equal an odd number. So we're going to find that, in fact, that length and width is going to be one different from one another, since we want the most square rectangle that we can produce so that we can optimize the area and the perimeter. From this, we're going to find that length is equal to the ceiling of 2 times the square root of 2d over 2, and width is going to be equal to the floor of the ceiling of 2 times the square root of 2d over 2. So now we're going to get into the domino arrangement itself. So we're going to be referring to the restricted case from here on out, because in the non-restrictive case, the arrangement is fairly trivial, as you can just stack the dominoes on top of each other and adjacent to one another. So for our non-restricted case, we're going to first consider the corner arrangement and work our way from there. So in the corners, we see that we can either fill a corner with a Z shape or an L shape. We can see that the Z shape creates some amount of gaps in the bottom left and the top right, and that the L will fill that bottom left corner, but does create some sort of gap above it. So now we should consider how many gaps does the L shape consider when we stack them on top of each other. And in the next part, we can see that if we stack the L's on top of each other, some amount of gaps are going to create, where we start with one L, we have 2 gaps, and if we add one more L to that, we're going to have 4 gaps. So every time we add an L on top of each other, more gaps are created. So that begs the question, exactly how many gaps are created from either using the Z shape or the L shape? So if we look at when we have 2 dominoes, if we have 2 dominoes, we have exactly 1 gap in the center, and we have the dominoes in a sort of box around that initial gap. So what we did from here is we developed a technique for arranging the dominoes to attempt to minimize the number of gaps. We can see that below the 4 images that the dominoes are kind of layered around this initial square, and there's either 2 or 4 or 0 gaps that are created in this arrangement. So this is we call this a spiral technique, where we kind of spiral the dominoes around one another until the box is filled, and once the one layer is filled, you just add another layer and continue building. So this begs the question still of exactly how many gaps are created. So we know that in the center of this arrangement, we're going to have at least 1 gap. So the area in our restricted case must be at the very minimal 2 times the number of dominoes plus 1. So using techniques that we used before, solving for length and width in the non-restricted case, we're going to use for the length and width in our restricted case. But now our area changes from the square root of 2d, or our area changes from 2d to 2d plus 1. So the length and width stay the same, except that inner ceiling is going to change from 2 times the square root of 2d to 2 times the square root of 2d plus 1. So now we're going to have to do a little bit of solving with floors and ceilings. So we can see that with our length, we're going to have a ceiling nested inside of a ceiling. So in terms of inequalities, they're going to stay the same throughout. However, with our width, we have a ceiling nested inside of a floor. So our inequalities are going to change a little bit as we solve for the inside and the outside of the ceiling, but eventually we are going to be able to solve for some sort of inequality that will give us a formula that we can use. And in this case, X is going to be the size of the dimension, and D is going to be the number of dominoes. So with those inequalities that I just showed you, we're able to create this sort of table that allows us to check it for a number of dominoes and then compare the dimension size from the length and width in the non-restricted case to the length and width in the restricted case. So let's start by looking at 2 dominoes. We can see on the left side, if we have 2 dominoes, we're going to have a dimension size of length 2, and the width in our non-restricted case will have dimension size of 2 for 2 dominoes. However, in our restricted case, if we plug in 2, we're going to find that the length is going to equal 3 and the width is going to be 2. So now we see that the length is differing, and we have dimensions 2 by 2 versus 3 by 2. Obviously, the perimeter is going to be different in that case. So for 2 dominoes, we have that the perimeters will differ. So now let's look at 3 dominoes. If we look at 3 dominoes, we're going to have the length is going to be, of the non-restricted case is going to be 3, and the width in the non-restricted case is going to be 2. However, in the restricted case, we have that length is going to be 3 and width is also going to be 3, therefore being different. So we can go through and look at all for like the first handful of differing values, and we're going to find that the length is going to differ at 2, 8, 18, 32, and so on. And eventually we could find that D is actually can be rewritten as 2 times some number squared, which we called A. And so length will always differ when D can be rewritten as 2 times this A squared. And the width we're going to have differ at 3, 6, 10, 15, 21, and so on, which we saw was a binomial expansion of A choose 2. So when D can be rewritten as A choose 2 for some number A greater than 1, the perimeter will also differ there. So in conclusion, we use floors and ceilings to move the optimized solution into our integer field, and then we developed a technique of our spiral arrangement to arrange the dominoes for our restricted case. And from that technique that we developed formulas that allows us to use inequalities to solve for floors and ceilings. And then eventually that resulted in us finding that whenever D can be rewritten as 2 times A squared or A choose 2, the perimeters would differ. Are there any questions?
Any questions for Evan?
Yeah, I have a question.
Go ahead.
Evan, do you consider this, like, is this something that you would submit or are going to submit to, or do you think it needs a little more? Like, what's the status of the work right now?
So we have to finish writing it up, but then we're going to submit it to Math Horizons and like reach out to them. The publication for the original question already came out, but we'll reach out to them and coordinate with them.
Oh, yeah. There's more than one way to skin a cat, right? Okay.
Okay, Dr. Marlowe.
Yes, I'm probably a little slow, and it's probably very easy to show that A choose 2 is never 2 times A squared. But that would be just worthwhile saying if it's true, which I believe it is.
Okay. Yeah, I don't think it's ever true. I believe, yeah, I don't think it's ever true, but yeah, I can make note of that.
Okay. Thank you so much, Evan.
Of course, that's A and B for the record. They can't be the same A, obviously.
Right. Yeah. A just represents some integer. So whatever, you can plug in any integer into that, and that would be the solution.
Okay. Thank you so much, Evan. So now we have 2 more groups. We have our junior seminar groups. So Father Laracy, I think you wanted to say a few words before your group's presented, so go ahead.
Thank you, Tara. It was my privilege to be able to lead the junior seminar this semester. Our topic was dynamical systems theory, particularly looking at nonlinear systems using qualitative techniques, building off of concepts in analysis and topology to study some very interesting nonlinear systems. I came across this quote actually yesterday from Poincaré, one of our founding fathers in this field, so I thought I would share it with the group. Our textbook for the junior seminar was Dr. Steve Strogat's book, Nonlinear Dynamics and Chaos. I really enjoy this book, and I think it was good for both professor and students to guide us. So the junior seminar this year, as I said, was focused on the field of dynamical systems. A lot of the systems we examined were continuous. We modeled them with differential equations, although we did also look at iterated maps. We began our study with one-dimensional systems, looking at local behavior, looking at flows on the line, bifurcations, flows on the circle. Then we moved up to two-dimensional systems, looking at the phase plane, limit cycles, revisiting the notion of bifurcations, and then finally going to higher dimensions, the emergence of chaos, and finishing up with strange attractors and fractals. Throughout, I tried to introduce issues of computability, simulation, and applications. And in addition to online resources, we made extensive use of Mathematica and Vensim to explore different solutions numerically, to create visualizations, and to run simulations. The 4 students in the seminar were very, very hardworking. They're very talented, and I'm proud of their final projects, which they'll present now. Thank you so much.
Thank you. I think our first group is William and Donna.
All right. Can you see it?
Yes, we are all set.
All right. Today, Donna and I will be presenting our research on sleep cycles with implications on productivity for college students. As Father Laracy said, this was a project for a junior seminar class. All right, so first we're going to talk about dynamical systems, some more kind of put them in context. We're going to talk about mathematical models of sleep, specifically the two-process model described by Ackermann and Ortberg. We're going to talk about ordinary differential equations, which we're going to call ODEs, and some analysis of the sleep cycles and our Vensim model that we developed. Some of the motivation behind this, one of the first assignments in this class was to create a simple sleep model. And you can see on the slide here, this was the original idea threw together. A lot of this stuff we weren't able to go into because the simple system itself is very complex. But this was kind of the motivation behind it and the interest in sleep. So going into dynamical systems, a dynamical system is a mathematical formalization that describes how one state of a system evolves into another with the passage of time. And these systems can be solved analytically or numerically, and one can predict the future state of the system in these ways. Some examples of this include mathematical models that describe the swinging of a grandfather clock or pendulum. And these two equations at the top on the right of your screen describe the two-process model. S sub t describes the homeostatic pressure, which is basically the tiredness you feel. The top portion is, it describes how your homeostatic pressure decreases while you're asleep. And the tau sub d you see in that equation is a time constant, which tells you how much sleep or how much homeostatic pressure you're losing for a standard amount of time you spend asleep for decreasing. And then in the bottom part, or the bottom part of that equation, you can see the rising homeostatic pressure while you're awake with this time constant tau sub r. And the COT equation is the circadian process that you're all probably familiar with. This is a mathematical representation of it, where A sub I is the amplitude of the 5 harmonics. They're basically self-correcting, and they're different for each person. Phi there is the circadian phase, which is the offset of sleep time. So H naught that Don is going to refer to is a variable constant. It's our mean tiredness or your initial tiredness. We looked specifically at a period of 1 day. So we were able to vary the H naught on our own at initial time because we're not looking at a longer period. But the final two equations there explain upper and lower bounds, H plus and H minus, as functions of time that induce both sleeping and waking when your homeostatic pressure reaches those limits.
Okay, so in regards to the original research that we came up with, we looked at how exercise and stress affects the previous variables that we'll discuss. So the effect of exercise on H naught is that H naught will actually raise by acute when you have acute exercise. H plus will lower by chronic exercise, and H minus, the slope of it will either flatten or it will be lower. So when it comes to sleep, exercise lowers your REM and raises non-REM, and non-REM will, if it's raised, it'll lead to a better circadian process, which we want. The tau d sub d and tau sub r will are based on the quality and the amount of sleep. It affects the time constant there. So stress, we noted that stress is self-correcting based on human factors. So it's individual, depending on a certain individual. Stress will affect everybody differently. So therefore, the variables can either increase or decrease based on that specific individual. And what is this relation? We want to look at the relation to productivity. So because sleep is related to different traits of an individual person, the amount of productivity of an individual is also based on their individual traits. Therefore, to establish a link between our productivity and sleep, there must be a certain initial conditions depending on the specific traits of the individual. Now, when you go to model this, it's difficult to model the effects of different traits because each trait has a significant effect on sleep and productivity habits, which makes each different individual person different than the next. So in the graph posted on this slide, we created the graph in Mathematica, and if you look closely, you could see that there's a globally attracting stable point. So this graph models the two ODEs, which are also on this slide. So they both go towards the point 0, 1. W is the waking function of T, which is depicted on the x-axis, and that's the top equation. And then S is the sleeping function on T, which is depicted on the y-axis and is the bottom equation. Because these points are converging to 0, 1, it is asymptotically stable. So this means for wake, it would always go towards 1 and sleep would always go towards 0. So we're using Vensim to model these. We're using Vensim to model these equations. So Vensim is a software that shows our dynamical systems model. Specifically, Vensim is a simulation software that supports continuous simulation with some discrete event and agent-based modeling capabilities. So we're going to see in the next slide how we model these. So these are our two models that we developed in Vensim. We built two flows for the ODEs described in the previous slide, and we graphed the changes in rates which could be seen on the slide. So the model on the left shows the homeostatic pressure increase rate flowing to the accumulated pressure while awake, and the model on the right shows the homeostatic pressure decrease rate flowing to lost pressure while asleep. So the homeostatic pressure increase rate shows that even though pressure is continuing to accumulate, it rises by less the longer you are awake. So we want to note that this is actually longer than you would sleep in a given day, what we're looking at. So from this slope, we can see that it's still accumulating close to the same amount of homeostatic pressure the longer you are awake. And in regards to the homeostatic pressure decrease rate, it shows that you sleep for a shorter amount of time, but the effects that sleep actually decreases the longer you are asleep. So in other words, basically you get less value of sleep the longer you are asleep. And for the two ODEs on the previous slide, this shows what they'll look like for various H naughts and times. So for the future, we want to look more into productivity, and we eventually want to develop a more complex Vensim model. And then we also want to study the impacts of stress mathematically if we could model that in a certain way. So these are just our references and acknowledgements. So we wanted to thank Father Larissy for the support and guidance he gave us throughout this project, and also Dr. Luttrell for her input and expertise. And we wanted to thank the whole of the College of Arts and Sciences as well as the Department of Math and Computer Science. Thank you.
Okay. Questions?
Yes. John Masterson asking a question. The book that started this process was the book by Steve Strogat. What was the title of that book?
It's called Nonlinear Dynamics and Chaos.
Yes, I'd like to make a comment. It's a very interesting field. Steve Strogatz, when he finished his bachelor's degree in around 1983, then over that summer before he started school, became a student of at least of Arthur Winfrey. Arthur Winfrey was the pioneer in studying biological clocks. That was his big area. Arthur Winfrey wrote The Geometry of Biological Time, and he was both a mathematician and a scientist who studied circadian rhythms and biological kinds and made tremendous advances. For instance, he was the discoverer that certain kinds of cardiac arrhythmias, reentrant arrhythmias like ventricular tachycardia, atrial fibrillation, could be caused by spiral waves in the heart muscles. Arthur Winfrey was sort of the for Steve Strogatz to go on to graduate school in dynamical systems. If anybody wants a reference in which Dr. Strogatz talks about his inspiration from Dr. Arthur Winfrey, I'm going to send that short article to them. Thank you very much.
Thank you. I see we have a question in the chat, and then I see Dr. Marlowe has a question. So let me head over to Annalisa's question. She asked, is there a specific productivity or performance model you plan to use?
Yeah, so we talked a bit about the homeostatic pressure and circadian process equations on this slide. So the productivity model we're looking at has to do with, well, actually more specifically, these W and S equations that are used here in these ODEs. We're looking at those as functions of time in conjunction with the circadian formula in order to create more of a neurobehavioral performance model based on these equations from Aherman and Bordbellier.
Okay. So then we'll shift over to Dr. Marlowe's question.
Oh, very simple in this case, but personal experience, one thing that is an interesting variable for your initial graph, it would be interesting to take into account, is allergies, which is a sort of stress, but a little bit different.
Yeah, definitely. Something I forgot to mention, but an interesting aspect of this is that the two-process model kind of replicates the PR model, which is another way to represent sleep. It's named after Philip Robinson, and they devised a model that describes the neurobehavioral performance on a in depth. So there's some research that kind of bridges the gap between this two-process model that we're working with and more of the scientific description that this relates to.
Okay. Thank you, William and Donna. Job well done. That will bring us to last but certainly not least, Lucas and Louie.
All right, good afternoon, everybody. So I'm Louis, and my partner Lucas will be presenting COVID-19 SER-IR model. We're gonna be talking about the SEIR model, three different variations of it. The most basic, which is the SIR, where the people that recover from COVID won't become susceptible anymore. The second version would be the SIRS model, where it's basically the same as the SIR, but the recovered can become susceptible again to COVID. And then finally, we'll talk about the SEIRDB model, which as the recovered, after being recovered, people could, after being infected, people could recover or die. And then those that recovered have the option of getting vaccinated. So, yeah.
Sorry. The first part is what are SIR models. So they're a basic model that shows the spread of disease from susceptible, infected, and recovered, as seen in the graph on the top right. And so based on this, we developed some basic differential equations here for S, I, and R, susceptible, infected, and recovered, where the beta was the infectivity rate and gamma was the recovery rate. So to analyze these equations, we had to first reduce them to two-dimensional equations. So when we did this, we got these two equations here, and then we used data from Seton Hall, where we found a infectivity rate of roughly 0.1135 per week, and then we had a recovery rate of 0.99 through the CDC, and we used these in our equations to model these equations. So fixed point analysis of the SIR model. So we used these equations, we found the fixed point, and when we found the fixed point, we noticed that at I equals 0, where I is the y-axis. You can see all the arrows are going into the y equals 0, which shows that in this model, no matter how many infected, eventually it's going to go to 0. Eventually, the COVID will end. And so here we are calculating the eigenvalues through the Jacobian matrix to analyze the fixed point, which was the line. So we put this into the Jacobian. We found the partial differentiation for different factors. And again, we plugged in our data where we found a positive eigenvalue and one that is 0. When these actually indicate that it's a neutrally stable fixed point. Again, I'll show the graph where, so all this entire line, so this whole line is all fixed points here. And each one of these fixed points is Lyapunov stable, or they're neutrally stable. So the COVID-19 will not become endemic in the SIR model where people cannot become reinfected. So now we're going to go into a model where people can become reinfected, which is SIRS. So like I said, people can become reinfected, which is this arrow up here. So in our model, we added a minus CR and a plus CR, which provides a rate for how fast people from recovered are able to go into susceptible. So we had to reduce these again to two-dimensional differential equations where we created these two differential equations, which are minus ASI plus C times, this was just R. We switched that out for N minus S minus I. And the I differential equation, which is ASI minus BI. And again, we plugged in some data from Seton Hall, and we used a resusceptibility rate, you could say, of 0.001. This is one of our assumptions in this model. And what's good about this model is that, say you don't agree, with this 0.001, you could plug it in, you'll get a pretty similar graph no matter which point you plug in. So stability analysis of infected and recovered. So if we set both of the equations again to 0, we find there's a fixed point at 8.722 for S and 2.363 for I, which you can see right here. So then we again calculated eigenvalues for the SIRS model through the Jacobian matrix, and when we found these, we got two complex eigenvalues. And when you have two complex eigenvalues, it indicates that there's a spiral sink, which you can see here, which is a spiral sink model, which shows that when people can become reinfected, the COVID-19 will be endemic.
So this is the equations that go into a SEIR DV model, which you could see we added the death equation and a vaccination equation. So we basically did the same type of analysis for an SEIR-DV model, except for analysis purposes, we reduced it to 3 equations instead of all 6. And we used the susceptible, infected, and recovered. So computing the Jacobian for this 3D model is basically the same as the SIRS, except it's a 3x3 matrix. And we basically follow the Jacobian way of finding the matrix, which is just the partial derivatives of S for column 1, the partial derivatives of I for column 2, and the partial derivatives of R for column 3, following the distinct equations. So the first row would be the S equation for susceptible, the second row would be the infected equation, and the third would be the recovered equation. And we found 3 different eigenvalues, all of which are negative, which indicated an asymptotically stable fixed point. So we created a 3D phase diagram, and basically all the arrows point to a fixed point, which means the virus is eradicated, which means at some point the virus will no longer exist within the population. And you can see that as the as the infected goes lower, closer to zero, the infection will be terminated. So the SCR-DV simulations we did through Benson, and the first picture shows low death rates, high recovery rate, and low transmission rate. And you can see how vaccination at some point plateaus to around 2 per week. And the death rate is really, really low throughout like the whole 80 weeks that we ran the simulation. And then, so we wanted to show like some parameters. If we change some parameters within our model, it's going to have a huge effect in what the outcomes are. And the second picture demonstrates that with, we kept vaccination the same at 0.1% or at 1%. And what we changed was the death rate from 0.01 to 0.51. We reduced the recovery rate from 0.99% or 999% to 0.01, and we increased the transmittance rate from 0.11 to 0.33, and clearly that really affected the model. As you can see, the vaccinations went down per week, the deaths increased, and the number of exposed people became a little bit less due to the fact that more people were dying, so less people were, so the population was decreasing. These are limitations that we had to, that affected our model, which was the population mainly, because Seton Hall is a very busy community and a lot of people come in and out. And that really we couldn't have like a fixed population. So we focused on a population of a dorm in the campus. And we would like to thank Father Joseph Larcy for his help throughout the semester and with our research project. And these are our references. And I appreciate your time. Thank you, guys.
Thank you. Questions for Lucas and Louis? Dr. Marlowe.
Everybody deserves at least one question. So the issue is, if you're exposed, okay, you could still you could still in principle become vaccinated if you don't know you've been exposed. So what effect, if any, would that have on the model?
So if exposed could go to recovered essentially without passing through infected is what you're saying?
No, yeah, well, you could be vaccinated while you're exposed, which has two problems. The first is that there could be an interaction, but that's a medical issue, not a differential equations issue.
Mm-hmm.
But if you don't know you've been exposed as a practical matter, you may get vaccinated.
For that issue, I guess we could probably put in another factor for our exposed. Maybe put like a rate of. It's difficult to even determine a rate of.
I know it's just something to acknowledge as an open question, I think.
Okay. All right. Thank you, Louis and Lucas. Job well done. So, yes, nice work, everybody. So I just wanted to say thank you to all of our students for their wonderful and interesting research this semester and all of the hard work. I know I'm not alone when I say job well done. You guys always you guys never cease to amaze us. I wanted to thank everybody for attending our math, computer science, and data science presentations and supporting our students and joining today. Before we go, I just want to, just thank Dr. Marlowe one more time and our media specialist, Burke, for helping everything run so smoothly and for everybody's input and help in me organizing this. So that being said, I hope everybody has a great rest of your day and a wonderful weekend. And thank you, everybody.